4.6 Lesson 2, Differentiability and Continuity. In Lesson 1, we learned about this property, differentiability implies continuity. If function f is differentiable at x is equal to c, then it must also be continuous at x is equal to c. And we also learned about conditional statements. So this is a conditional statement. We have P implies Q, where P is called the hypothesis and Q is called the conclusion. And if you write not Q implies not P, that is called the contrapositive of the conditional statement, and they are what we call logically equivalent. If one is true, the other one is also true. So the contrapositive of this conditional statement would be the negation of the conclusion. So we write, if the function f is not continuous at x is equal to c, then this implies the negation of the hypothesis. Then the function f is not differentiable at x is equal to c. So these are true statements. The converse and the inverse of this property are false. In the converse, you have Q implies P. This is false for this particular conditional statement. And the inverse would be not P implies not Q. And that is also false. So the converse is false. So if you could have continuity at a point, but it does not imply differentiability. And the inverse is false. If a function is not differentiable at x is equal to c, it could be continuous, maybe not. We don't know. This is what we learned in Lesson 1. You will understand the relationship between the differentiability of a function at x is equal to c and the continuity of the function at x is equal to c, and you will be able to use the relationship to determine differentiability or continuity of a function at x is equal to c. Today's example will look at Objective 3. Given a piecewise defined function, you'll be able to determine whether the function is differentiable at the x value that divides the two pieces. And when we look at our example for today, we will be using this property to help us with it. So here is what you have to understand about continuity. Continuity is necessary for differentiability, but it is not sufficient for differentiability. What that means is the following. We know that if a function is not continuous at x is equal to c, then it is not differentiable at x is equal to c. So for a function to be differentiable at x is equal to c, it has to be continuous, but this by itself is not enough to know that the function is differentiable at x is equal to c. Because you could have continuity, but maybe the function is not differentiable at x is equal to c, maybe it is. But it is a necessary condition for differentiability. We will take a look at example 4. The instructions are: use one-sided limits to find the values of the constants a and b, which I wrote in red, that make the piecewise defined function f differentiable at x is equal to 2. Now what is significant about x is equal to 2? That is the x value at which the defining rule for the function changes from ax cubed to b times x minus 3 squared plus 10. So we need to figure out what the values of a and b should be so that the two pieces will connect smoothly at x is equal to 2. Because that's what's going to make sure that because they connect, they will be continuous. And remember, continuity is necessary for differentiability. But the next thing that we've got to make sure is not only do they connect, not only is the function continuous at x is equal to 2, but the two pieces connect smoothly so that we also have differentiability at x is equal to 2. Remember, continuity is necessary for differentiability, so we've got to make sure that we've got continuity at x is equal to 2, but it is not sufficient for differentiability. So after we make sure that we have continuity at x is equal to 2, we also have to make sure that we have differentiability at x is equal to 2. So here's how we're going to do the problem. We will begin by making sure that the function is continuous at x is equal to 2. And then we will make sure that the function is differentiable at x is equal to 2. In other words, we make sure that the two pieces connect at x is equal to 2, and then we make sure that the two pieces connect smoothly at x is equal to 2. How do we make sure that the function f is continuous at x is equal to 2? So we have to go back to the definition of continuity. So how do we make sure that the function f will be continuous at the point where x is equal to 2? We have to make sure that all three of these conditions are satisfied. So we have to, 1, make sure that the function is defined at x is equal to 2. It is defined at x is equal to 2. You can see here that we have if x is less than or equal to 2, this is how the function is defined. So you would just have 2 cubed is 8. You would have 8 times a. That would be the value of the function at x is equal to 2. So this is satisfied. The important thing for our work is we have to make sure that the second condition is satisfied, that the limit of the function as x approaches 2 exists. And we also have to make sure that it is equal to the value of the function at x is equal to 2. But that will happen. So we've got to make sure that the second condition will be true. How do we make sure that the limit of the function will exist as x approaches 2? We have to consider one-sided limits. We have to consider what happens as x is approaching 2 from values that are less than 2, and what happens as x is approaching 2 from values that are greater than 2. So we have to consider the left-sided limit of the function and the right-sided limit of the function as x is approaching 2, and then we've got to make sure that the two one-sided limits are equal to each other. That will guarantee that the limit of the function as x approaches 2 exists. So we're going to make sure that the function is continuous at x is equal to 2. We would consider the limit of the function as x is approaching 2 from the left and make sure that that is equal to the limit of the function as x is approaching 2 from the right. So the limit of the function as x is approaching 2 from the left. If x is approaching 2 from the left, x is less than 2, so we would use the rule for f of x, that is ax cubed. And then you can evaluate this one-sided limit by direct substitution, where you will substitute 2 in place of x. So 2 cubed is 8, and you get a times 8, or 8a. And now you will consider the limit of the function as x is approaching 2 from the right. So if x is approaching 2 from the right, x values are greater than 2. So the rule that you need to use for the function is b times x minus 3 squared plus 10. And you take the limit of that function as x is approaching 2 from the right. You evaluate this limit once again by direct substitution. You will replace x with 2. So you get 2 minus 3 in the parentheses. 2 minus 3 is negative 1. Negative 1 squared is positive 1. So you get b times 1, which is just b plus 10. And of course, for the limit of the function as x approaches 2 to exist, the left-sided limit and the right-sided limits have to exist, and they have to equal each other. So we get that 8a must be equal to b plus 10. So we have this equation. But you will observe that this is one equation. We have one equation, but we have two variables. So we cannot solve this unless we have a second equation that would also relate A and B. If we can have a second equation with A and B in it, together with this one, we will have a system of two equations and two unknowns, and then we would be able to solve that system of two equations and two unknowns by using, for example, the substitution method. So how do we get a second equation for this problem? Again, continuity is a necessary condition for differentiability at a point, but it is not sufficient. You've got to consider whether the pieces connect, but you also have to consider whether the pieces connect smoothly at x is equal to 2. So how do we make sure that the two pieces connect smoothly at x is equal to 2? Here's what we're going to do. We've got to make sure that the function f is differentiable at x is equal to 2. And the way we can do that is by taking the derivative of the function one piece at a time. So take a look at our first piece. We have ax cubed. We can use the power rule to take the derivative, and we will have 3ax squared. And we're going to write if x is less than 2, even though in the original function it's less than or equal to 2, because we can talk about one-sided derivatives, but maybe we haven't done that, so we're just going to not consider the derivative at the end point, x is equal to 2. But of course, that's okay because we have the other piece, and that's going to also be happening at x is greater than 2. So they will come together at x is equal to 2. So now you take the derivative of the second piece. Again, you're going to use the power rule here. And the derivative of the constant 10 is 0. So you're going to have 2 times b times x minus 3 to the first power. And then you have to use the chain rule as well. X minus 3 is your inside function. So you multiply by the derivative of the inside function, but that is just 1. So you don't need to show anything. So this is happening if x is greater than 2. So how do we make sure that the function f is differentiable at x is equal to 2? We've got to make sure that the left-sided derivative at x is equal to 2 will be equal to the right-sided derivative at x is equal to 2. The way we show that is by taking the limit of the derivative as x is approaching 2 from the left, and then taking the limit of the derivative as x is approaching 2 from the right, and making sure that these two limits are equal to each other so that we will have differentiability at x is equal to 2. So for the left-sided limit of the derivative, we write the limit of, if x is approaching 2 from the left, then this would be the derivative of the function f. So we have 3ax squared, and we take the limit of that as x is approaching 2 from the left. Again, you evaluate this limit by using direct substitution. Substitute 2 in place of x. 2 squared is 4. 3 times 4 is 12, so you get 12a. And here, what happens as x is approaching 2 from the right? This is the rule that you have for the derivative. So you have the limit of 2b times x minus 3 as x is approaching 2 from the right. And you're going to, again, evaluate this limit by using direct substitution. Replace x with 2. 2 minus 3 is negative 1. 2 times negative 1 is negative 2. So you have negative 2 times b. And again, you've got to make sure that f is differentiable at x is equal to 2. So the left-sided limit of the derivative and the right-sided limit of the derivative at x is equal to 2 must equal each other. the one-sided limits at x is equal to 2, the one-sided derivatives at x is equal to 2 must agree. So we're going to write 12a is equal to negative 2b. Now you can simplify this a little bit by dividing both sides of the equation by negative 2, and that would isolate b on one side, and on the other side 12 divided by negative 2 is negative 6. So this is our second equation. b is equal to negative 6a. Our other equation is 8a is equal to b plus 10. So now we have a system of two equations and two unknowns, and we may solve this system of two equations and two unknowns by using the substitution method. So here is our system of two equations and two unknowns, and we will solve this system of two equations and two unknowns to find a and b that would make our piecewise defined function differentiable at x is equal to 2. So we already have that b is equal to negative 6a from the second equation. We can substitute negative 6a in place of b in the first equation. So when we do that, we will have 8a is equal to, in place of b, you can write negative 6a plus 10, and you can add 6a to both sides of the equation. 8a plus 6a would give you 14a is equal to 10. Divide both sides of the equation by 14. You get a is equal to 10 divided by 14. And you can reduce 10 over 14 to 5 over 7. So we know a should be 5 over 7, but what should be b? What should b be? So to figure that out, you take a is equal to 5 over 7 and substitute for a in the second equation, and that would give you b is equal to negative 6 times 5 over 7. So you get b is equal to, that's negative 6 over 1 times 5 over 7. That would be negative 6 times 5 is 30 over 7. So that's what b is, negative 30 over 7. So now that we know what a and b should be, I can go back to my piecewise defined function and replace a with 5 over 7 and replace b with negative 30 over 7. So these are the values of a and b that would make the piecewise defined function f continuous at x is equal to 2, meaning the two pieces will connect at x is equal to 2, and furthermore, the two pieces will connect smoothly at x is equal to 2, making the function f also differentiable at x is equal to 2. As a last thing, we will check this by looking at the graph of this piecewise defined function, which I have done on Desmos. So let's take a look at how the graph of f would show up, how it would look at x is equal to 2. We want to see specifically that with these values of a and b, the two pieces will connect at x is equal to 2, and the two pieces will connect smoothly at x is equal to 2. Let's see that now. So you enter the piecewise defined function into Desmos as you see here, and this is the piece for when x is less than or equal to 2, and this is the piece for when x is greater than 2, and Desmos will show you the graph of this piecewise defined function. The first piece for values of x that are less than or equal to 2 is shown in red, as you can see here. And what happens at x is equal to 2? Do the two pieces connect? The red piece does connect with the blue piece, and not only do they connect, but they connect smoothly at x is equal to 2. So not only do we have continuity at x is equal to 2, but we also have differentiability at x is equal to 2. So we found the values of a and b that would make the function f differentiable at x is equal to 2, and we checked our answer by graphing. Today we focused on Objective 3. Given a piecewise defined function, you will be able to determine whether the function is differentiable at the x value that divides the two pieces. And of course, we know that continuity at x is equal to c is a necessary condition for differentiability at x is equal to c, but it is not sufficient to guarantee differentiability at x is equal to c. In looking at this problem, we also reviewed what we learned in Lesson 1.